some reason, I think a lot of people in this class are going to the other two because they're both pretty full. We are doing a type of model that is also in chapter 5. So the transportation models we did on Tuesday and these models today are in chapter 5, and they have identical structure to them, okay? So the way that you set them up as either matrix or list, that part's gonna be the same. What's different about them is the context of the problem. So we know what we were doing in a transportation problem was trying to get, to ship something or send something from a source location to a destination location. You had multiple ones, and so that's why you had the matrix. And usually what you were doing in transportation was trying to minimize cost. You wanted to do it in the most cost-effective way. So we're gonna have a similar thing structure-wise, but the context is that you're trying to assign something to something. So you still have that like matrix setup, but you're trying to assign jobs to workers is gonna be our first one, contracts to contractors, we're gonna do one classes to professors. So you're assigning something, and you're assigning something. It's not like source and destination anymore, but you've got the two different things, and that's why you have that sort of matrix style setup. And there will be different measures. If you think about it, when we had a transportation problem and we had the blue matrix, it had the cost associated with that path. So in our first problem here, what we have in that blue is the time to complete the job, because we're trying to assign jobs to workers. And so how much time does that person take doing that job? Okay, so every combination of how much time does it take that person to do that job. That's what you'll have in the blue matrix. Then the class professor one, it'll be one where we're looking at a satisfaction rating. But in this first one, it is actually a book problem, not one of the examples in the chapter, but one that's at the end of the chapter. So it's problem 70 from chapter 5, but we'll have all of everything on the spreadsheet that you need. Okay. And we'll actually do, well, honestly, I've got them written on here, and I don't know if they come from the book and I just wrote them on there myself so I wouldn't forget to do them, or if they were ones we added on to the end of it, but we'll do a little analysis after we solve for it. Okay. Then we're gonna do one that is trying to put professors' classes into certain time slots, and the blue matrix is their satisfaction rating score, for those different times, like how they feel about the different times. And we have to offer a certain number of classes and all this. So we'll get to that. Oh, well, that's the blue matrix. So how do they feel? This professor, would rather do 9, 10, and 2 tie, 11 and 3 tie, So that's their satisfaction ratings there. And that'll be on the worksheet as well. This one is actually very small, but we use it to show iterations of the same problem and the consequences that come out of solving certain things certain ways, and the unintended consequences that come out of solving stuff. So that one will be kind of interesting, because after we solve it, it's going to be super simple to solve it. And then once we do that, we're going to start looking at, when you make these changes, what just happened? How do you accommodate for that? That's what's going to happen in this problem. All in all, we'll finish a little bit earlier so that we have time for me to show you how you would set these problems up if you had to set them up yourself. Okay. So we'll do that right at the end. Okay, so here is this problem that comes from the textbook. And we've got 10 employees and 15 different jobs that need to be assigned to these employees. Now each job only needs to be done one time. And so some people, obviously, since we have 15 jobs, some people might do 2, some people might just do 1, so we'll look at that. But there is I know this is tiny, but you've got it in front of you, so that's good. The max that we want anybody to do is 2 jobs. But so that's why you see the 2 up here. But we want to make sure every job gets done. Okay, so that's going to be the other constraint. These are basically going to be the 2 constraints. Okay, I'm going to do something right now that you can do too if you want to. It's going to help me when I get to the part where I'm setting up solver. So when you see empty cells in here, that's because that employee can't do that job. Okay, basically what we were referring to as disallowed paths. It's a disallowed path, just like when a plant couldn't send to a certain distribution center. Well, these are ones that can't be done. So I'm going through as carefully as I possibly can, I am picking up, when I'm selecting, you'll see why in just a second, I'm selecting all these disallowed paths. I want to make sure I don't forget one of them. And I'm shading them a little bit differently. I want them to stand out. The reason I want them to stand out up there is because I want to recreate that same pattern down here in the red changing cells. Trust me, this one's a little more interesting to do. Kind of take your time and be careful, because if you mess up, you have to do it again. We don't want that, so. We'll find out in just a second. Trying to recreate that exact same pattern down here, because, yeah, okay. Essentially, those are the disallowed paths. Those are ones that I have to account for. I have to do something in Solver to say don't use those. You know, don't use those people on those jobs, those employees on those jobs. And so I'm kind of visually double checking this again, because I need to make sure that it's right, because that's gonna be, you know, it's gonna set me up for whether or not the problem solves correctly or not. But once I've done this, okay, once I've done this, you'll see where that comes into play when I'm doing Solver. The other part, the filling in the spreadsheet, the cells and everything, I still have to do kind of all the normal things that I would do in these types of problems. One of the things that I'm going to be doing is making sure that any given employee doesn't get more than, if you look back up there, doesn't get more than 2 jobs. Okay, so what do I have to do there in cell Q24? Because basically I have to figure out how many jobs they have so that I can constrain it not to be more than 2.
So?
Yeah, I just need to sum. So it's just like before, you sum the rows. And that, of course, is true for everybody. Everybody's going to have to make sure, for everybody that they don't do more than 2 jobs. So over here under the maximum, I'm going to reference that cell. I want to reference that cell because I don't want to just hard code it in there. If it's in one place, I can use it. In fact, you'll see that we will use it in a few minutes. So I want to reference B3, but I want to make sure that's an absolute reference to B3. And this particular worksheet doesn't have the logical operator on there. I want it on there because it looks better, it helps me later. So what should the logical operator be between how many assignments they have and what the maximum is?
Less than or equal to.
Yeah. So that should be a less than or equal to. Okay, so that takes care of essentially what is one of the 2 constraints. One of the one that says you can't do more than any given employee should have more than 2 jobs. This one is going to take care of the making sure every job gets done, and only once, but make sure it gets done. And so on job assignments, as I look down, jobs, I'm basically going to do the same thing, right? I'm going to sum this column because I want to make sure that every job gets done. Now let me explain real quick what's going to be in not these cells that I'm going to have as disallowed paths, but what's going to be in all of these other cells is either 0s or 1s. They either get that job assigned to them or they don't get that job assigned to them. They get the job, they don't get the job. It's just like, or they get the contract, they don't get the contract. Teach the class at this time, don't teach the class at this time. So those will be 0s and 1s in all of these spots. And what I'm trying to do is make sure that this adds up to, exactly every job is completed 1 time. Now I have that information up above, so I'm gonna reference this cell, assignments per job cell, absolute reference it. So I'm doing an absolute reference to B4. absolute reference to B4, so that when I accumulate or sum up how many jobs did they get, that it is exactly, not how many jobs did they get, how many times did the job get done, okay, that it's exactly once. I want it to be done exactly one time. And then, okay, and then the overriding, objective here, because those are the times it takes the employee to complete that job. So the objective in this is that we're going to assign the jobs in such a way as to minimize that overall time, that we'll be as efficient as possible. We'll get the jobs done as fast as we possibly can, okay? And so my time to complete all the jobs, what do I put into this objective cell? Yeah, sum product. And that's true of all of these. I mean, they're all gonna be like that. And it's the sum product of these blue, in this case, time, and the red, which is the assignment, whether or not they get a job. So remember, what's gonna happen is, this is gonna have zeros and ones. So when we're multiplying every one of these, obviously the zeros, it doesn't get, it's zeros product and nothing adds into the total. So it's just for every job that actually gets assigned, we will know the total time. And our goal is to minimize that total time. Okay, so this part is not hard. I mean, last time all we did was sum product, and this time we had to throw some logical operators in there and reference a cell. So, but this is not, this is not a difficult problem from that perspective. But when you have a problem like this, with all these scattered disallowed paths, we now have to look at, when we're setting up Solver, how different it's gonna be. Okay, so when we go into Solver, our objective is to do what? Minimize that total time. So the total time's in B38, and we wanna minimize it. Okay, so once we get that in there, we wanna minimize B38, so that's definitely what we're doing. We have the choice of the two things that we can do to account for all these disallowed paths. One of them would be when we get to the point where we're doing constraints, go into every one of those and say this has to be equal 0, this cell has to be equal 0, this has to be 0. In other words, you can't assign that one, okay? That's one way. I'm gonna go ahead and show you the other one. The other one is the one where you select around, where I was telling you, you have to actually make sure those are not changing cells. So I actually have to select around these, which is why I shaded them like this. Well, actually for either one of those things I would have needed to shade them, because I was gonna need to specifically do something to those cells, either set them to 0 or not include them in changing cells. So this time I'm gonna not include them in changing cells. But just real quick so that you know, I'm sort of methodical about the way I go through it, but at the same time kind of efficient. Like I'll do the first one, hold the control key, and start doing all the rest of it. And I usually just kind of do it column by column, but when there's two together, I'll try to do two together because I want to be a little more efficient about it. So to select these changing cells, what I'm gonna do, I'm gonna do this, put the control key down, and then go to work carefully, but hopefully efficiently, selecting all the ranges, which do not include the cells I highlighted. And take your time. Take your time and be careful, because it's a pain in the butt if you don't. I mean, it really is. It's like, oh, if you mess up, you have to start over. That's no fun. Okay, so it takes me a minute, but I eventually get all those selected. There is a limit to the number of different ranges that you can have, and I've had students do this not as efficiently, and I think they bumped into the limit. Like they were trying, like instead of doing columns 2 and 3 together, would have done just 2 and then 3. And they started to get too many little sections. I don't know why. Oh no, we're not even there yet. Okay, so I get these changing cells in there, and they are tediously entered, but I'll show you how you'll know. I'll show you how you'll know if you got it in there correctly or not. Okay. But we do need to add the constraints. So the constraints, Well, we just talked about what the constraints were. The constraints are that we can't let someone do more than 2 jobs. So when we look at how many jobs an employee is assigned, which is in Q 24 to 33, that has to be less than or equal to the maximum number, which you find in S 24 to 33. Okay, so Q 24 to 33 less than or equal to S 24 to 33. That's one of them, and the other is to make sure every job gets done. And so now that's B to P 34. Now, I guess you could say greater than or equal to, knowing full well it's not going to sign it more than once because they're trying to minimize time. In this particular case, just the context of it, I think I would go ahead and just say equal. We know it has to be exactly equal to everything getting done one time. So I would say B to P34 has to be exactly equal to B to P36. I would put the equal on this one. I did, I did it in the, and those are your only 2 constraints. Again, I'm not sure why this got turned into nonlinear. Turn that to simplex LP. But you're minimizing B38 by, I've selected all of it, by changing everything except those highlighted cells. So I selected all the way around those, and then put my 2 constraints in, make sure they don't do more than 2 jobs, and make sure every job gets done. Solve it with simplex LP. And we've discovered that it's gonna take a total time of 263 minutes to complete all those jobs. Okay. This is the problem though, that maybe makes you appreciate this a little bit more, okay? Because whether you decided to take those cells and set them to 0, or whether you had to work around them, it's a little more tedious. It might be that you'd just rather have done this in the list form. Now granted, somebody else set the list up for you, but in the list, you don't have any of the disallowed paths. So like you don't see 1 to 6, you don't see 1 to 14, you don't see 2 to 6, or 2 to 9. So if it was a disallowed path, see, it's not in here, okay? So since it's not in here, it makes some of the other things that you're gonna do a little bit easier. I will say though, just so in the interest of time, I had already named these columns, and so in your file, these columns should be named, and they're named the heading you see on the column. So this data is employee, job, time, assignment. Okay. Because this part, I do realize, instead of just some product and you're done, you do have to do what function here in order to calculate how much has been assigned to a given employee. What function do you have to do instead of sum? What do we do on the transportation problems? We have to do a sum if. Is that awful? No, it's not. I mean, you have to think about it a little bit more, perhaps, okay? But it's not awful. You do now have to say, well, what's the range that you're looking at to match the criteria? So what are we looking at first? What's the range we're looking at first to match the criteria? The employee. Because we're looking for employee, in this first line, we're looking for employee 1. And we're summing what?
The
Assignment. Okay, so the idea is, whereas in a matrix we could just sum up the row, and that told us how many assignments that employee got, here we do a sum if, look to see for each employee, first it starts with 1, how many assignments they got. Okay, sum of how many assignments, same idea. And because the columns were named, I don't have to worry about absolute addresses on that column A or that column D. I don't have to worry about that. The G7 is a reference to employee 1, which I do want that to change. On the next row, I want it to be 2, and then 3, and then 4, all the way down. So that's the good part. I don't have to worry about dollar signs. And I do that sum if. And I do the same sort of a thing to accumulate how many times the job was done, because we're actually gonna force it to be done exactly once. So I do another sum if, but this time I'm looking at what range?
Good job.
I'm looking at job, and I'm still summing, you know, whatever job it happens to be, and I'm summing, not based on whether the job it is, but what am I summing?
The assignment.
The assignment still. And if you think about it, if you think, well, we're summing assignment there and we're summing assignment here, yeah, and in the matrix, you summed it two ways too. You summed it by its rows, you summed it by its columns. You summed it based off of employee, you've summed it based off of job. And the reason, of course, why we're doing this is to make sure that every job gets done exactly once. And our total time is still what? It's still a sum product, and this time, I mean, not this time, but it's the sum product of what? Time and assignment, which is the blue and the red, just like it was when it was in matrix form. It's just in a list column form, but it's the sum product of time and assignment. So if somebody else does the work to set the list up, you know, if you go to the trouble to set the list up properly, yes, you now do sum if, and sum product as opposed to sum and sum product. Okay, but that's not that bad. And here's where it makes it easier, right here. You go into solver, and all this gets easier because now you didn't have disallowed paths anywhere in the list. So you just straightforward, your objective is to minimize the total time. Okay, that's in H37 now. So your objective is to minimize H37 based on changing what? Assignment, yeah, which is the red cells, you know, the changing cells. It's even easier because we named it than us having to drag, you know, and do the range, but in any case. And then we still have the exact same two constraints. Make sure the employee totals H7 to H16 is less than or equal to the maximum amount that we want any of them to do. So H7 to 16, less than or equal to J7 to 16. And right now the max is that they can't do any more than 2 jobs each. And let's make sure every job gets done. That is the accumulation of the jobs, you know, whether it was assigned or not. H20 to 34 has to be equal to J20 to 34, which is that we want every job to be done exactly 1 time. So it's just the 2 constraints. And I don't know, that again is nonlinear, not sure why, but it is. So we're minimizing H37 by changing assignment, the red cells, the changing cells, subject to these 2 constraints, okay? Don't do more than 2 jobs, make sure every job gets done, solve it with simplex LP, and we absolutely should get the same answer here. And if you don't get the same answer, then something's weird, because these aren't 2 different problems. This is the exact same problem. We're just solving it using 2 different structural, you know, methods here on the worksheet, but it's the exact same problem. The result, the who you assign the jobs to kind of thing, should be exactly the same, therefore the total time should be the same. So here's the thing about this though, if you look at this, and you look at that result on, oh, I told you I would tell you this, I should have done it right after the last one. If you do this method where you kind of highlight those cells that should be NA cells, as long as you don't see a 0 or a 1 in any of those cells, then you're good, okay? As long as you don't see a 0 or 1 in any of those cells, then you're good. Every other cell should have either a 0 or a 1. Because if you had a 0 and 1 in one of these, it would mean you forgot to exclude it from the changing cell area. If you have another cell that doesn't have a 0 or 1 in it, then you accidentally excluded it when it shouldn't be. And that's how the shading kind of helps you figure out if you got everything in there right. I mean, it's just a little helpful there. Okay, but, should have said that before. What is the consequence of, what is something that happened with this solution that you may not have wanted to have happen? employee without an assignment. If you look at employee number 6, all the way over there, you'll notice that they didn't get an assignment. Well, we didn't specifically say that that was not okay. You know, that wasn't a part of our model. We might have just assumed everybody was gonna get one, but us assuming it and it mathematically being forced to happen are two different things, you know? So we might have thought it was gonna happen, but it didn't happen. And we specifically put measures in place to make sure no one got more than 2, but we didn't put anything in place to make sure everybody got a job. Okay. So that's one of the things that you sometimes do, you know, after you solve something, you look at it and you go, wow, we have an employee without a job. That wasn't the intent. We want every employee to get a job. We don't just now suddenly go pick somebody else's job and give it to them. No, we resolve it with that being a constraint, you know, because we want the best solution. We just want everything to be accounted for that might need to be accounted for, okay? So, this is what I do. You do not have to do this, but I'm just saying. I've learned over time things that will make things go faster, and I don't insert, in this particular instance, I do not insert new columns because of the shading and it's messy. So here's what I do. I would take this whole section right here. I would do a Control X to cut it, move over 2 columns, and paste it back in. Because what I now need to put in that I didn't have in there before is a minimum. I need to say everybody should get a job. And I didn't say that before. So I'm kind of just doing a little setup on my worksheet to include a minimum, which of course would be less than or equal to what's assigned. Okay. Didn't want that cell. Okay. All right, so I put this in. I tried to center that. Okay, I put that in, and I've taken everything that was already there, cut it and repasted it 2 columns over. And my reasoning for doing this is not that you have to do this, is I like the way it looks. I like the idea that I'm sandwiching this in between its minimum and its maximum, okay? So like it's really clear what's going on here. This number has to be greater than or equal to the minimum, less than or equal to the maximum, that it's sandwiched in here. But I also don't want to now turn around and just put ones all the way down that column. I want to add, okay, I'm gonna put a new row in. You don't have to do that if you don't want to. But I'm gonna put a new row in here that there's a minimum assignments per employee. You know, that I should have accounted for the fact that that was something I really wanted to have happen, is that everybody would get a job, okay? So minimum number of assignments per employee, and I'll reference that here. For me, that's in B5. I'm absolutely referencing it. So you can see when you add a new constraint in, you can see if you already have something in there that's currently violating that constraint. Okay, we do. We have this one in here that if you look across here, it was currently in violation of that constraint. Okay. Oh, I thought I was gonna sneeze. All right. When I have one that's currently in violation of that, when I impose a new constraint or I tighten a constraint that we currently have, my objectives, is it gonna get better? No, it can't get better. It could stay the same, but it's probably gonna get worse, which in our case, worse would mean taking more time. Okay, and so it's likely this is gonna take more time, but we'll find out. But after I've done all the adjustments to the worksheet itself, I now have to do what? With that new, that's a new constraint. I gotta get it into Solver. I have to get that new constraint into Solver. So luckily, things stay in here and I don't have to redo all that selection process, which is a real pain. All I have to do is just add a new constraint. So I'm gonna add a constraint that says that this minimum has to be less than or equal to the employee assignment. Now, the way that I've done it, this is now Q 25 to 34, less than or equal to S 25 to 34. And the other one that I had in there before scooched over and it became S 25 to 34 less than or equal to U 25 to 34. So anyway, I just added that new constraint that wasn't previously in there that I didn't think about. You know, I just didn't think about the fact that somebody wasn't gonna get a job. So when I solve this now, as expected, my time goes up. You know, it's gonna take me 10 minutes longer because I had to give this very slow employee, I don't know, you know, I guess they're slow, that's why they weren't assigned any jobs. But I have to give this slower employee a job, and now it's gonna take 10 extra minutes. Now, you know, nothing is in violation of any of these constraints now. Some people have one job, some have two. We don't have a lot of room to play with here. We have 10 employees. We just said they all have to have a job. There's only 15 jobs, so there's only 5 kind of extra ones to play around with and assign to people. But that might make us think, oh, no, before I do that, let me show you, it's just as easy to do that over here as it was in the matrix. And here's what I would do. I would grab all that. I would grab all this, Control X, cut it, move over, put in a min that I didn't previously have, because I didn't previously have a minimum. Actually, I want to reference that up here as well. So I have this new min jobs. I started to abbreviate on the second sheet. Okay, so I have this new minimum number of jobs, which is 1. Make sure everybody gets at least 1. I referenced that here. I took the time to just, because I like the way it looks when I do that, I took the time to take this stuff from here, scooch it over, so I could put these 2 new columns. And I didn't insert columns though, because that would have messed with the stuff down here. But I'm referencing that new minimum job cell, absolute referencing it. So just as easily in the list form, onto the spreadsheet, I've included this new constraint, but I don't just have it on the spreadsheet. I've got to go into Solver and add it into Solver as well. Okay, so add that new constraint in that now says this minimum of 1 each has to be less than or equal to how many jobs they are assigned. If you put it in the same place as mine, it's H 8 to 17 less than or equal to J 8 to 17. When we solve this, again, what happens? Well, time goes up because we're using somebody we didn't want to use, but it goes up exactly the same as it did in the other one because these are not 2 different problems. Okay, so anytime we would get a different number in that would not be a good thing. So when I had this one out and I said, you know, it's kind of interesting, you don't have a lot of jobs to play with. You've got 15 jobs and 10 people, and you said everybody had to have one, so you've got these 5 extras. But it kind of makes you wonder, once they all have 1, what if we hadn't said they couldn't have any more than 2? What if there's just one really fast person, and so, you know, they could have 3, 4, 5 jobs, you know, they're just that fast. So we want to give them the opportunity to do that. Well, we could easily go into a solver table and check that out, okay? So if we went into solver table, to run solver table, we could vary that max number of jobs right there. I mean, why did we decide 2? I mean, it makes some sense in a lot of ways. You don't want to just overload anybody, but hey, what would it help us if we did? As long as everybody got at least 1 job, you know, let's let some other people have more if they're faster. So B3, the max jobs. Oh, I hit enter after I moved here. Okay, max jobs, and then we'll start with 2. And take this up to about 5. I don't think we're going to give anybody 6. But anyway, and do that in steps of 1. Okay, so let's say we left open the possibility they could do 3, 4, 5 jobs if they were the fastest people at the jobs. What would I look at as output to see if I'd accomplished, what I was trying to accomplish there by letting them have more?
Den times it complete.
Yeah, because what we're looking at is is it faster if we let a particular person or a couple of people have 3 jobs instead of just 2? Could we get that time down, to even faster? So B3, vary it from 2 to 5 in steps of 1, and look at what that does to the total time in B39. And what it does, this is a really small solver table, which is amazing, this goes this slow, is it gets better if we did bump that max up to 3, but after that it doesn't. Now, so I can see that, and I don't need to go to 4, and I don't need to go to 5, but if I decided to go to 3, I'm still not gonna know what the solution should be unless I go back and resolve it and change that max to a 3. Because I don't right now know is there just one person who gets 3 or a couple of people who get 3? I wouldn't know. I don't know from this solver table solution. I don't know that. I just know that if I would bump that max up to 3, I could save 2 more minutes, okay? And so I might want to rerun it and see what that solution looks like. You also have to remember that we're also still solving this on the model where we're making sure everybody gets 1 job. What if we took that constraint out and then bumped this up to a maximum of a really high number, 15? One person does all of the job, that kind of thing. How would that change the time? So there's a lot of different analyses that you could do on this. You could look and rearrange it in different ways, but that's all. But that's all we're going to do for this one right now. Questions about this? Questions about this problem? This one is more to, well, getting used to the idea of an assignment problem, the zeros and ones, kind of assignment, non-assignment thing. But it's also to let you see the scattered disallowed paths and what do you do with them and how it looks. It makes you appreciate the list just a little bit more, because the disallowed paths aren't in the list. But anyway, that just gives you a little of that. Plus, the whole idea of modifying it when we determine that there's a new criteria, a minimum that we hadn't thought of before. But I want to move into the professor assignment problem. It's almost like we're taking a step back, certainly size-wise to this problem, we're taking a step back because this is a lot smaller. But we're using this smaller problem to see how, as we do iterations of changes, how that impacts things and unintended consequences and what we have to do to account for those. Okay. So starting out, what you have are 3 professors and 6 different time slots. And it turns out that every professor is going to be teaching 2 classes. And so that works out nicely because if you have 3 professors teaching 2 classes, that's 6 classes. And it would be really nice if we spread those 6 classes out in our 6 time slots. I mean, why would we overlap and cause conflicts when we have exactly the number of time slots as we would have classes? So that seems like a good idea to make sure that will be one of the constraints, that make sure every time slot actually gets a class in it. Okay? But we also need to make sure that the professors teach exactly the number of classes that they're supposed to. So you see the information up here that you're going to be referencing, but the first thing, and I won't even ask you again, is that, because it says it on there, you need to sum up this row so that you can make sure that it is less than or equal to how many classes they need to teach. No, not less than or equal to. No. Equal to. Because if we do less than or equal to, then we might have us 2 classes. But anyway, so that is equal to the required number of classes that they'll be teaching. Okay. All right. Now, all of that was needing to be copied into the other things, so I just kind of doing the quick method here. But we're summing up each professor's classes, making sure that's equal to the required number of classes, which is 2. We do want to make sure that we spread the classes out in those 6 time slots. So we're going to sum up what gets taught at any given time slot for all time slots, and make sure that that equals one class per time, which we've got up here, a reference to one class per time. So on this one, I've actually am doing the not doing calculations, but I'm referencing cells that have the constraint input values in them, 2 classes per professor, 1 class per time slot, making sure that when I've summed the rows and summed the columns that it matches that. And then here, for their total satisfaction, I don't think I even talked about what this was. I did another class, I didn't think I'd say it here. But the way that we're assigning them classes is to try to achieve the highest total satisfaction rating. And so they've each, I've said it I think when we were on the PowerPoint, but I didn't say it after we got it here. They've each rated those class times by the higher the better. They'd rather teach at the ones they give the higher ratings to. Okay. All right, so this is what I'm going to try to maximize, the overall satisfaction rating. So that's going to be, like it always is, the sum product of those ratings that they gave to the classes. And then, of course, what's in here is zeros and ones, right? They either did or didn't get that class time. And so once I multiply that by the ratings, I'll get an overall total satisfaction. Now, I am going to do something here real quick, and it's not the objective function, but I'm going to do a quick calculation for the average satisfaction. Because in a minute, that's going to make a difference for us. I mean, it's going to be useful to us to have an average satisfaction, which is simply just going to be the total satisfaction divided by the number of classes. I'll sum up how many classes there are. Because again, this stuff is going to start changing as we make little modifications to this model. So the total satisfaction divided by how many classes there are, that's the sum of J15 to J17, that'll be the average satisfaction. That'll be an important number to us if we want to be comparing apples to apples, you know, we'll see in a minute. Okay. We did the usual. There aren't even any disallowed paths in here. So I'm really telling you, this is really a step back to solving this so that we can look at the changes that are going to come out of it. So let's just real quick do a solver on this. Our objective is to do what? Maximize total satisfaction, which is in B22. So B22, maximize that by changing, well, always the changing cells, but whether or not we assign professors to class times. B15 to G17. So maximize B22 by changing B15 to G17 and add the normal 2 constraints that are on your columns and your rows, but what it is here is that every professor, the amount of classes they teach, that's in H15 to 17, has to be equal to the required amount, which is in J15 to J17. So H15 to 17 equal to J15 to 17. And then add the other constraint that makes sure that we are balancing out our class schedule so that every class time, B to G18, is equal to, what the classes in that time are equal, it's equal to 1. Okay, B to G20. No disallowed paths, it's super easy, it's got 2 constraints, everything about it is a pretty simple problem. And when we go to solve it, we get a solution, everything is good. And this is the solution. You know, you can see where everybody's teaching. This one might end up not being as happy as they thought, but you know, nevertheless, this is where everybody's teaching, right? So all of that is good. Their total satisfaction 46, average satisfaction 7.66, repeating. And then, things are always changing. We have twice the enrollment we thought we were gonna have. So we're gonna need twice as many classes, and everybody's gonna have to teach 4 classes instead of just 2 classes. Okay, well, 4 classes. Okay. Now, with 3 professors teaching 4 classes, we have 12 classes and 6 time slots. So now we have to have how many classes for each time slot? if we're still wanting to be very balanced about this. Okay, if we're still wanting to be very balanced about this, then we have to double up how many are at each time slot also, if we're not gonna expand the time slots. Okay, so we just switched that from 4 to 2, and you see those changes reflected here, so obviously we have to resolve this. And when you go into Solver, everything about the problem is fine. We haven't changed anything that would require Solver to be different. We've simply updated a couple of the input values, which happen to be the constraint values. Okay? So we've just updated those. So all we have to do now is just run it again. This is why we needed an average, because it would look like they're twice as happy now, which I can assure you, teaching twice as much, they're not twice as happy. But the average is still the same. But what do we see in this solution set that doesn't make sense? Probably isn't practical.
You can't teach two things at the same time.
Right, so here's what happened mathematically. If the best solution originally was for this person to teach here and here, and this one here and here, and this one here and here, well, when you doubled it up, the best mathematical solution was just gonna be to double them up at the exact same time. I mean, that's mathematically what made the most sense. It's obviously not practical, and so when you see something like this, you say, oh, I didn't think about that happening. There needs to be another way to constrain the problem so that we understand that that can't happen. Okay, so there is another thing that we needed to consider, and that's the classes per professor per time. You know, I mean, let's think about it. That obviously has to be a constraint that we weren't really thinking about. And now we've got to take that into account, that you can't double them up at the exact same time. You have to make sure that there's only one, essentially that these are just zeros and ones. Now, one way to do this is to make this binary values, and that's fine too, it really is. But putting this constraint in makes it descriptive of why we're doing what we're doing, is because they can only have, you know, one class per professor per time. Okay. But I've just put that there. I haven't really done anything with that yet. I need to go into Solver and add that as a new constraint. And that's a brand new constraint that wasn't there before. So we add a constraint that says all of these values right here, all the changing cell values, have to be less than or equal to 1. I can't make them exactly 1, or exactly, because they're gonna be zeros and ones. But they do have to be less than or equal to 1. So make sure all of those are less than or equal to 1. So a new constraint. Is my objective gonna get better? No, I mean, it's probably gonna get worse. I mean, we can check and see, but when we solve it, and we now have, you know, the 4 classes in there, to make comparisons, well, that did drop from 92 to 87 because of the same number of classes, but it's easier to look at the average, which is 7.25, which is down from where it was before. But obviously this one makes sense. And the other one didn't make sense. You couldn't do that. You couldn't have them doing that. But things are always changing, and so we suddenly discover that, oh yay, we're not gonna have to teach. We're gonna just use a little bit bigger rooms. And we're not gonna have to teach 4 classes. It's just gonna be 3 classes. So if I go up and change that value up there to 3 classes, it's reflected here. If I went straight back into Solver to solve this, just straight back in, I've changed an input, which is a constraint value, changed it to 3 instead of 4, and go back in and solve it, I'm gonna get this. So this is not feasible. What I just tried to do is not feasible. Why is it not feasible? And you can usually pick up on why something's not feasible by looking at the constraints that are not currently being met. And kind of put it together. why wouldn't this work? Why couldn't I just shift them down from 4 to 3 classes under the current model? Well, what's not being met right now?
The classes per time.
Yeah, the classes per time. Because
Because it, a lot, like it collides with professors, classes per professor.
no, because they had, a minute ago, they had 4 classes, and it all fit, and everything was okay. Now they only have 3 classes.
Would it be the best way to, I guess, maximize satisfaction?
No, I mean, that's always just gonna happen, you know, I mean, that's always gonna be the goal in this problem, is to maximize that.
There's not enough classes.
Right, so when we had 3 professors teaching 2 classes, and that was 6 classes, we perfectly had 1 for each time slot. Then we said, no, there's gonna be 4 classes for each. Well, now we have 12. We perfectly had 2 classes for each time slot. Now we just shifted back to 3. 3 professors teaching 3 classes is 9 classes being taught. Okay. It doesn't fit with, 6 time slot thing. So we've got to modify this constraint to not say equal, but to say less than or equal. Because it can't equal 1, that'd be 6 classes. It can't equal 2, that'd be 12 classes. Some of them will be 1, some of them will be 2, so we just need to change that to say less than or equal to. Now, it's one thing to change it on the worksheet, but I obviously have to go back in here and find that one. That's the one that has B to G 18 being compared to B to G 20. Go in and say change that one, and change it to less than or equal to. Okay, so I actually have to go in and modify this constraint that already existed, but to say less than or equal to. Once I do that, it's going to solve now. I mean, now it's not gonna have a problem. Their satisfaction rating got average, got all the way back up to what it was initially when they were just teaching 2 classes. However, we might have gotten a little unintended consequence here as well. What happened here that maybe we don't want?
Nobody in the 3 p.m.
Yeah, so the 3 p.m. time slot doesn't have a class. Well, we've been working really hard to say balance everything out. You just fully use all the time slots. We understand that some time slots were what we thought would happen. Some would have 1, some would have 2. We get that. We weren't anticipating that one of them would not have a class assigned to it at all. And so now we've got this, probably should have thought about this, but a minimum classes per time. So we didn't have to think about it before, because before we were exactly making it 1 and we were exactly making it 2. So we never had to worry about, trying to cause something to have a minimum. But now we really do have a minimum number. If we're still trying to balance out the classes over the 6 time slots, okay, then we probably should put a minimum classes per time in there. Once I do that, I've got the whole model modification thing I kind of have to go through here. This is how I would do it. Again, just in time, I've learned I don't like to add rows and columns because of what it does with the shading. So what I've learned is grab the stuff you want moved, Control X, move down 2 rows, Control V, so that I can put in a required minimum, because this one's more like a required max. And I'm messing with the worksheet here, I'm messing with it, I'm changing it to, have all the things in it that I need. Okay, so I took what was here, this, which used to be here, moved it down here, so that I could get this new required minimum in there that I didn't have before, my less than or equal to signs. Why do I do it that way? Because I like to see this sandwiched in between its minimum and its maximum. If you have another way you want to do it, that's okay. It's okay, you have to still be able to accomplish this. But anyway, we need to, after we put it into the worksheet, of course, we've got to understand that that has to go into the solver model as a whole new constraint, a new minimum constraint. So, oh, sorry, I didn't put it into the model yet. I didn't reference the cell that I needed to reference. Reference that one up there, actually absolute reference that one. Okay, sorry, that needs to be in there before I go into solver, so put that in there. Now I'll go into solver and add that constraint here that wasn't here before, that minimum of 1, okay, to be less than or equal to how many classes are at the time slot. And again, we've got one that's currently in violation of that before I even press solve or okay and everything else. And so therefore, this is probably gonna get worse. Likely it's going to, because we're gonna ask it to do something it didn't originally want to do. We now have 4 constraints in here where we started this problem with just 2 constraints. And then we solve it, and yeah, it got a little worse. But we do have what we kind of were thinking all along, is that 3 of the time slots would have 2 classes and 3 of the time slots would have 1 class, which is as balanced as we can get it when there are 9 classes. So here are the steps that we kind of went through here. It was a super simple problem. When we doubled up on what was required, classes and classes per time and classes per professor, when we doubled up on that, it automatically doubled up on where it was when we realized that, practically speaking, that couldn't happen. And so what we needed to do was go in and make sure that all those assignment values were 0s or 1s. In other words, put a constraint in that said those all had to be less than or equal to 1. Could have said binary, but less than or equal to 1, either one. And then, when we went back to 3 classes, we realized we had constraints in there that were in there in such a way that the equals just, it wasn't gonna work, okay? So we had to switch that to a less than or equal. As soon as we switched it to a less than or equal to, though, we ended up with a class without a time, a time without a class, that's the way I meant to say it. A time without a class, and it's like, uh-oh, that's not what I intended. Just like I didn't intend originally for one of my employees not to have a job, okay? When you know that that's something that you wouldn't want to have happen, you build it in, but the problem is you don't think about it necessarily in the beginning. So when you solve models, what you have to do then is go back and look at them and say, do these solutions make sense? Are these solutions accomplishing everything I wanted to accomplish in the way that I was thinking that it would happen? And when you see things like that, like there was a time that didn't get a class, there was an employee that didn't get a job, you just realize sometimes you just have to build extra constraints in to take care of things that you hadn't originally thought about having to build constraints into, So that's kind of what this model is all about, is going through and doing that, and going through these little iterations of things. Okay, so questions about that, because I wanted to leave some time for me to show you some other stuff. But I want to make sure we get all the questions answered that go with these assignment problems. Either, obviously they're looking a lot like the ones we did on Tuesday. So I'm actually going to switch back over to a file that has transportation because it's easier to work with this. I pulled a little piece out of the plant and distribution center problem, okay, because I didn't want it to be as big as it was to do what I'm going to do right now and show you this. If you had a transportation problem and you had, oh, it doesn't start like, well, I don't know what that number was originally. Oh, I can figure it out.